My name is Jenny, and today I wanted to do a very quick video just demonstrating HAWCStab2 and how you can use it to calculate structural eigenanalyses of a wind turbine. I'm not going to go into a lot of detail of what HAWCStab2 actually is or how it works, but I will explain in general. It's an aeroelastic tool that is produced by DTU Wind and Energy Systems, and it does not actually do time marching simulations, but what it does do is essentially steady state calculations and different types of eigenanalyses. And today we're going to focus on one of those eigenanalyses, which is the structural eigenanalysis. So this is the eigenanalysis that only takes into consideration the mass and stiffness parameters of your system. It doesn't include any aerodynamics and it doesn't include any controller. But let's go ahead and just demo it and show exactly what it can do. So for those of you who aren't familiar with how to work with HAWCStab2 at all, essentially it's just an executable. So I'm going to locate that executable, which is here in my folder. So I'll open it. And now you can see my HAWCStab2 window comes up. So I'm going to open my model file. So this is a standard HTC file. I'm going through this part quite quickly because I'm assuming that people are mildly familiar with HTC files and all of that. If not, you'll have to check the manual, get a bit familiar with that background. So here is the DT 10 megawatt file. I'll go ahead and open it. Now you see a little confirmation up top. Has opened the command file, and presumably there were no errors, otherwise it would have closed down. To do a structural eigenanalysis, it's very easy. Click on Computation, Structural Modal Analysis, and I have two options here. I can either do the blade only or the entire turbine. So we can start off by looking at the blade. I think that'll be fun. And I have two options. I can either do it versus rotor speed, so at different rotor speeds, or I can actually do it versus wind speed. So somewhere in my input file, I have linked to a data file that essentially tabulates at different wind speeds what is my rotor speed and pitch angle. For this blade one, I'll just look at 0 RPM, and 10 modes is a little high. I'll drop to 5 maybe. Hit OK. Now you can see a plot has come up. I have rotation speed down here, and my blade modal frequencies are here. So if we click on this one, you can see this window pops up. So this is my first blade-only frequency. This is my flapwise, first flapwise happening at 0.61 hertz, 0.49% damping, so very low damping, and it also tells me the RPM and the pitch. Now you can increase or decrease the amplitude, and there's also ways to rotate, which I'll be honest, I never remember those key bindings, but if I click Help, Key Inputs, let's see, Shift X and Shift Y is the rotations I want. So let's look at that again. Bring that video back over. Okay, so we just rotated around one axis, not quite the one I wanted. Sorry that the animation is so slow, that's my computer being a little bit overclocked. Cool, so now you can see very clearly flapwise. Very nice. You can also, so that was 0.61, we can look at the next one. So this one's edgewise, happening at 0.93 hertz, etc., etc. All right, close this. Ooh, my computer's really struggling. Internet, I need a new laptop. So blade-only frequencies, if we remember those two numbers, I'm going to write them down. We had 0.61 was the first flapwise blade only, and 0.93 was first edge. I'm going to remember those because as we get to our full system frequencies, those numbers will come up again. So now let's go ahead and do the full system Campbell diagram. So this time we're going to go back to our computation, structural modal analysis, and click entire turbine. And this time I'm actually going to do it versus wind speed. So again, we're saying do it for all of the wind speeds in this lookup table where those RPMs are and pitch angles are kind of encoded within that lookup table. So let's say I look at 15 modes, maybe that's a little high. 11, let's try 11. So now I have 21 points. That's again determined by this text file, which I'm not looking up, but I'm not opening, but is linked with the HTC file. So you can see this is a little bit slower. Okay, and now after a few minutes, this structural Campbell diagram has been generated. So now you can see instead of rotational speed, we have wind speed at the bottom x-axis going from 5 to 25 meters per second, which is standard for the D2 10 megawatt. And you can see we have natural frequencies versus wind speed, and there's different behavior of different frequencies. I'm not going to go into detail of identification of wind turbine modes, so some of the terminology I'm about to use might be a bit confusing for you, but if you're familiar with concepts such as backward swirling or forward swirling, things of that nature, this should make a lot of sense. First and foremost, I want to note that this frequency down here is the rigid body frequency, so this is essentially the entire rotor turning at 0 hertz. I'm not going to look at that. We can ignore that one. These next two we have, if I open one of them, you can see that this is the fore-aft, the first fore-aft bending mode. So you can see the entire turbine is going forwards and backwards. Go ahead and close it. And that was, if I look and set it mode 3, we should expect to see the side-side motion. Sure enough, that's what we see. So the entire turbine swinging from side to side. Those two mode shapes relatively invariant with wind speed. And then we see several sets of mode shapes here where they essentially, you can see that they're kind of flat, and then either they go down like this one, or like this one they go up, and then they're flat again. This is actually because if you look at here's the lookup table, this is the rotor speed, the red line, for the D2 10 megawatt. So you see we have a minimum rotor speed, then we reach our optimal TSR tracking, so we have a linear relationship with wind speed, and then a flat rated rotor speed after. So again, yes. So again, those of you familiar with whirling modes can see that, well, this is a backwards whirling mode, so it's flat, decreases, and flat again. This one up here would be a forward swirling mode, flat, up, flat again. And this one is a symmetric mode. This is flapwise. I know because it's happening around 0.61 hertz, but I can also verify that by plotting it. So here we've picked our mode 5, which we guessed was a flapwise symmetric mode, and exactly we can see this very characteristic blades moving in phase forwards and backwards. So exactly as we suspected. If we pick this one, for example, this is our backwards whirling flap mode. It's a little hard to see because the animation is so slow because of my computer struggling. But you can see that the blades are deflecting now out of phase. So this one moves forward, and then this blade moves forward, and then that one exactly. So again, flapwise, first flapwise backwards whirling, first flapwise symmetric, first flapwise forward swirling. And here we have our edgewise modes, so they're both kind of equally centered about 0.93. We can verify that it's an edgewise mode by once again clicking on it and animating it, and sure enough we see edgewise motion, and then the three blades are kind of out of phase with each other. So each one is deflecting in an edgewise direction on its own time, so to speak. And lastly, those of you familiar with turbines will ask, well, where is the drivetrain mode? And that's a very good question. I have to remember. I think this is the drivetrain mode up at 1.78. Let's see if I'm correct. I am not correct. So the drivetrain mode is actually higher. It's actually at 1.81. So we can see that I don't have enough modes here to show the drivetrain mode. So we have to do it again, compute the entire turbine, and this time I'll change it to 12, not 132. That's way too many. 12 modes. To be safe, we'll do 14. So let's go ahead and generate this. All right, now we can see we have many more modes, and here is the mode that I wanted. So if we show this 1.81, increase that deflection, you can see we now have what's often called our drivetrain mode, so all three blades moving in or edgewise collective, if you want to call it that as well. So all three blades are moving in an edgewise motion with the same phase. So this is significantly higher than what we had for the whirling modes, which is pretty standard, I think, for blades, very long blades. And the last thing I just wanted to show is one of the cool things about a Campbell diagram is you want to be able to look at your p harmonics. So if I click on Tools and p harmonics, I can show 1p, 3p, and 6p, which are very important for considering vibrations, essentially. And with a 3p line, you can see actually why we have our minimum rotor speed with the D210 megawatt. That is explicitly to avoid this 3p crossing of the tower modes, in particular the tower side-side mode, because it's very lightly damped when you look at aeroelastic frequencies. It can be quite problematic if you have that crossover. So I think that's what I wanted to show really quickly. So again, very quick, practically oriented demo of how to use HAWCStab2 for identifying of structural frequencies, and a little bit on wind turbine mode shapes. So I hope this was useful. And yes, if you don't have a HAWCStab2 license and you're an academic user or a non-academic user, please do feel free to reach out to the HAWCStab team, HAWCStab2 team, those people, and see if you can get one. Otherwise, happy coding.